So next up, we have Shravan from Lagrange protocol. And just to kind of introduce a little, Lagrange protocol is building storage proof solutions across L1 and L2s. And some of you guys might have seen them presenting also at the SPC, but they recently released a paper about updatable vector commitment or something. So, well, I guess we'll learn more about it during the talk. So Shravan, feel free to take it over.
Am I audible?
Yes, I can
Okay.
hear you. Yes.
Thank you for the introduction, folks. I'm super excited to present our work in progress reg proofs. It's a Merkle tree-based vector commitment scheme, which has updatable batch proofs. So let's start from the basics. So what exactly is a Merkle tree? So a Merkle tree is a data structure that lets you compute a commitment to an ordered sequence of values. Say you have values A0 to A15 and a collision-resistant hash function H. In Merkle trees, you compute a commitment by recursively computing the hash of the adjacent pair of values. So you would take A0 and A1, compute a hash of it, concatenate and get the hash of it, and you so on do this for the other adjacent pairs. And once you have this, you kind of do this for this level of the hash values until you just end up with just one value, a single hash value. This single hash value is called as the root of the Merkle tree. Merkle trees are ubiquitous, and it has countless applications in blockchains and beyond. So in addition to just computing the commitment to an ordered sequence of values, and Merkle trees can help you help you prove that a certain leaf is in fact as a member of this tree. Say, for example, you want to compute, you want to prove that A5 is the member of this Merkle tree. Then what you would do is you would give out these specific values which are highlighted in green, which is A4, the commitment CLRR, and so on, and all the way until to the top is CR. So once you have these green values, any verifier can take this and can reconstruct the path from the leaf all the way to the root and compute and can reconstruct the digest of the tree. Given an unknown digest, a verifier can check if this reconstructed digest is indeed matches with what the verifier already has, and can decide to accept or reject this membership proof. The main focus of my talk today is about updates in Merkle trees and so on. So say that an arbitrary element changes in the Merkle tree. So this in turn affects the proof of, let's say for this example is in this example it's going to be A5. So whenever let's say for example A12 changes by delta, all we need to do is take the membership proof of A12 and recompute the path from A12 to the root. And in places where it intersects with the proof of A5, we just have to update those hash values. So thus, in logarithmic time, we can update individual membership proofs whenever there is an update, whenever there's an update in the Merkle tree. So we can continue to update all the way into the root, and we can also recompute the updated digest in the similar fashion. So let's delve into a special type of membership proofs called range proofs. So a range proof is essentially going to simultaneously prove the membership of multiple contiguous elements in the Merkle tree. Say you want a single proof which says that A3 to A8 is in fact in this Merkle tree. So to do this, first you would give out the membership proof of A3, which is going to be these values highlighted in green. And you will give out the membership proof of A8, which is going to be these values, which are also highlighted in green. So once you have this logarithmic size proof, what you can do is a verifier can take these proofs and the values if A3 to A8 and can check if in fact if this range proof is valid by reconstructing the hash paths all the way until the root. So just like an individual membership proof, you can see if the reconstructed root is in fact is what you already know. If that is the case, you accept the range proof, else you can reject it. Yeah, range proofs are also updatable in Merkle proofs and in Merkle trees. So whenever an arbitrary element A12 changes, it is very similar to updating individual membership proofs. So let's say A12 changes by delta, you update the hash paths from A12 to the root. And the places where the green node intersects with the path of A12 to the root, those values are of the range proofs have to be just updated. So once you update these values, you have the most up-to-date range proof, which incorporates the change that has happened in position 12. The focus of this talk is more about batch proofs. So a batch proof is a single proof to open k arbitrary elements simultaneously. So the key difference between a batch proof and a range proof is in batch proofs, it's going to be k arbitrary elements. However, in range proof, it's going to be a consecutive set of elements. A crucial efficiency property which we want from a batch proof is it has to be smaller than k individual proofs. As a naive way of doing batch proofs is you can simply concatenate the individual membership proofs of k elements and call it as a batch proof. However, that's why we want this special efficiency requirement. Existing approaches to batch Merkle proofs are not updatable, even when an element in the batch changes, or even when some other element outside the batch changes. Another thing which we touched in this work is aggregation. Aggregation is the process of simply combining multiple individual membership proofs into a single batch proof. So the more about what we have done in this work. So we present a updatable batch proof using recursive snarks for Merkle trees. And our batch proofs can be updated in logarithmic time, where n is the size of number of leaves in the Merkle tree. And we generalize this idea to do something called as verify MapReduce style computation, even when the data changes. Say that you have a bunch of leaves, and you want to say you want to have some sort of predicate applied on top of these leaves. Then using our approach, you can compute a simple snark proof, which essentially says, which can essentially attest to the predicate that was applied over these leaves. Specifically, we show how to do this MapReduce style computation in two specific applications. One is how to aggregate BLS keys, even when even when the data is changing. And how do we do a notion of the digest translation? This essentially argues that the Merkle tree computed using hash function, say SHA-256, or Poseidon over the same set of values, you can compute a simple proof to say that these two values are consistent. I'll dwell more into the details of these applications later in the talk, but the key point to note here is we can have all of these techniques work even when the data changes. So let me start with a notion of the naive batch proofs. Say that you want to compute a batch proof for elements A2, A4, A5, and A50. So the most obvious approach the naive approach to do is to just concatenate the membership proofs of A2, membership proofs of A4 and A5, and membership proofs of A15. So this is going to be a naive batch proof, but however, it doesn't meet the efficiency requirement. However, I'm going to use this as a running example for the sake of illustration for the rest of my talk. So once you have these naive proofs, we need to verify if this batch proof is valid. Any batch proof verification algorithm broadly takes in certain set of inputs. These are first, what is the digest of the Merkle tree? Then let's set S be the what is the subset of the claimed elements in this Merkle tree, and some characteristic about the height of about the tree. In this case, it's going to be the height of the tree, and some sort of auxiliary witness. So this is going to be the broad template. Almost you need to verify any batch proof regardless of how they are constructed. And the verification algorithm should spit out if true, if and only if S is indeed some subset of the Merkle tree of L height and whose Merkle root digest is C. And it should spit out no if S is not indeed a subset of this tree. In this talk, for the illustration purposes, I'm going to present two algorithms. The first one is the standard approach where you have individual membership, Merkle membership proofs. Using that as a witness, you can verify if the batch proof is in fact correct. And the second one is our approach. We use this approach in addition to the membership proofs. We also use something called as a node subsets, which I'll specifically precisely define later. We use additional witnesses to verify the same Merkle batch proof. So in the standard version, what you're going to do is say you have the A2, A4, A5, and A15 as a part of the batch, and you have the individual membership proofs. First, you check if A2 is in fact is valid. So you do this by reconstructing the path from A2 to the root, and you can check if this reconstructed root is what you expect as a verifier. Then you also verify individually A4 and A5 by reconstructing the root and check if this is in fact valid. And you do this so on for the other members of the batch, in this case A15, and you check if this in fact is the Merkle root which you expect. So obviously this mainly checks one proof at a time. Can we do better is what this book broadly tries to look. So this inefficient batch proof, which is essentially a concatenation of all the individual proofs, can be made into an efficient version. All you have to do is to just take the verification algorithm, and you can just simply snack it. So something like GROD16 would give you a small batch proof, and the single batch proof is essentially going to attest to the fact that certain elements were part of the batch, and and these elements are part of the Merkle tree, which has some Merkle root by just C, and so on. However, the drawback of such approaches are, so whenever there are changes to the elements in the batch or outside the batch, you have to recompute this proof from scratch. And another drawback of these standard snark-based approaches are you also need to have an a priori bound on total number of elements that are going to be part of the batch. So when you go out of bound, when your bound increases, you have to rerun the setup and have a fresh circuit for it, and so on, which is an additional overhead in these approaches. Our approach, a big picture motivation of our approach is how do we solve certain limitations which are there in the previous known constructions, and what can we do better is what is a big picture motivation. So say S is the set of elements that are in the batch. So we define something called as a node subset. So a node subset is essentially is defined with respect to the set S over which the batched elements are proved. So every node in the Merkle tree is going to have this value called node subset. So the way it goes about is, let's say that it's going to be a subset of values S, where at node B, it's going to be the values that are part of the subtree, which is rooted at V. I'll show this with a figure, which will become much more clear. So at the high level, what node subset does is it tries to have a set of values in each node. And these values are going to be a subset of the set S. And the values that are part of the subset are the ones that are present in that subtree. An obvious example of a node subset is going to be the root, which is essentially going to be the entire set S. To see this in a little bit more detail, you can consider this figure where let's say that as I mentioned, the node subset of the root is A2, A4, A5, and A15, which are these elements inside the batch. And let's say you take the right subtree. The node subset of this is just going to be the A15, as A15 is the only element from the set S that is part of this subtree. Similarly, for the left one, it's going to be A2, A4, and A5, and it does not contain A15 because A2, A4, and A5 are the only elements that are part of this subtree and which is part of the batch. So once you have this, a key thing to note here is in addition to having the Merkle hash values at nodes, we also have this node subset values in our construction. So the way we verify a batch proof naively in our scheme is first, we are going to prune out the set of nodes that are of interest to us in this Merkle tree. So these values are the ones that are from the root to all the way to the leaf that are part of the batch. So in this case, I'm going to iterate through an algorithm which is essentially going to look at all the nodes that are from the root and to values A2, A4, A5, and A15. So in this example, when we start from the root, first we check if the Merkle hash is indeed correct by hashing the left child and the right child. And we also check if the union of the node subsets of the left and the right make up the root. So in this case, it's going to be A2, A3, A2, A4, and A5 union A15, and we check this against the root and so on. So we can do this recursively to all the nodes that are of interest to us, and at each position we just make sure that the Merkle root matches, and the information about the subsets that is part of the node subsets are also indeed consistent. So we can do this all the way to the bottom. However, at the base case, the key thing to note here is we will have to check if the node subset of that specific leaf is in fact the content of that leaf. So and this is the only particular check which we have that ensures that the base case is correct, and you do this for all the elements that are part of the batch. So just like the way we made Merkle proofs, the standard naive Merkle proofs efficient by snarking, we use recursive snarks to do this. So I'm going to present you the circuit of how we do it. So it's going to take in the public input as the Merkle digest C, the subset, the batch subset S, and the height of the Merkle tree. And it's also going to take in witnesses, two witnesses specifically. One which attests to the fact that it takes in it's going to be the Merkle digest of the right subtree, the node subset of the right subtree, and the height of the right subtree, and a snark proof which says that this public statement with respect to the right subtree is in fact valid, and similarly for the left subtree as well. So the verification algorithm goes this way. First, we check if the height of the root is in fact is one above the height of its left and right child, and we also check if the Merkle hash value is in fact consistent, and we also check if the node subset of the right and the left tree when they are put together is in fact what you expect at the root. At the base case, we check if the data, the leaf data is in fact the node subset. And in the recursive case, we check if these are the internal nodes. In the recursive case, we check if the proofs that were came in as a witnesses, the pi L and pi R, if those proofs are indeed correct. And we do this recursively for all the nodes of interest us in the Merkle tree. To see this a little bit more pictorially, recall that this is the tree I have, which consists of Merkle hash values and the node subsets of what I've been showing before. The batch that is of interest to us is A2, A4, A5, and A15. So at each level of this tree, we are, except the leaf level, we are going to have a snark proof, which essentially attests to the consistency of the values that are in that specific subtree. So in this case, it's going to, I'm not sure if you can see the pointer. In this case, this proof pi LLR is going to attest to the fact that whatever went inside in this subtree is in fact consistent. And this is going to make sure that this subtree is consistent and so on. So we can recursively compute such snark proofs, which is going to attest to the other subtrees at which it's rooted. And we can do this all the way to the top. And at the root, you have the root snark proof, which essentially is a snark proof, which acts as a batch proof for the elements A2, A5, A4, and A15. So we call this data structure as a batch proof data structure. Once you have this data structure, whenever there's an element that changes in the vector, you can simply recompute the updated proof without computing from scratch. Say A5 changes by value delta. All you have to do is to follow the path from A5 to the root and update the witnesses and the snark proof that is there in each specific node. And we can do this all the way to the top, and you can compute the updated batch proof, which is pi prime in this example. So in this way, you can update proofs in logarithmic time rather than recomputing everything from scratch. Key optimizations which we use are, rather than passing around subsets as is, we use set accumulation, and we use hash-based set accumulation for efficiency reasons, and we don't need specific properties from it. So a hash-based set accumulation works perfectly fine for us. And we also have two separate circuits, one for the leaf nodes. So as you can recall, the computation in the leaf level was fairly simple. However, at the internal node, you also had to invoke expensive snark verification. So in our experiments, we actually break it down into two specific circuits, one for the leaf and one for the internal, and we put them together in a manner that consists it's cryptographically sound, and there are no scopes for attack. So this general idea of batch proofs, this idea can be generalized to perform map-reduced style computation. So let's say that you have A0 to A7. These values are committed using Merkle trees, and let the commitment be C. We can do, we can take the map values, we can map the leaf values based on some predicate that is encoded in the computation of map, and it returns the intermediate values to the level. The reduce operation takes these values together and spits out another value which can be further reduced all the way to the top. So at each level, the reduce operation is also attached with a snark proof, which essentially says that this reduce operation was done correctly over the data which has the Merkle commitment at that specific root value, that specific node. And we can do this recursively all the way to the top. And in the end, you can simply perform the reduce operation. This way, you get the result of the map reduce computation. At the same time, you also have a snark proof, which says that the Merkle digest C is the digest of the values A0 to A7, and the computation was performed correctly, and that is attested to using the snark proof pipe. So to see this a little bit more in the context of a real example, let's say that you have a smart contract with n memory slots, and each of that has n BLS keys. The goal is to compute the aggregated public key of a subset of people who have signed some particular message. And we also want to know that number of people who have signed, so that we know that sufficiently many people have signed a certain message. A key thing to note here is this subset can change over time, and such computations are useful in emerging blockchains and so on. So the exact statement which we prove is APK is the aggregated BLS public key of T public keys that belong to some Merkle tree of n public keys, and the root digest of that and BLS public keys is actually C. So say in this example, let's say that we have a Merkle digest over the BLS public keys of a slot A0 to 7, and say position 2, 4, and 5 sign a specific message. Then what we do in the map operation is, first we compute the number of people have signed, and at the leaf level, it's just going to be the 1. And the key that was used to sign, public key that was used to sign, is G raised to the specific secret key. And we can do this, and once you have mapped this value, you can perform the reduce operation at the successive levels. So in this case, if you look at the specific example, so since two keys have signed under the subtree, so the count is going to be 2, and the public key that is going to be there is going to be the product of these 2 keys. And there is not proof at each level, which will attest to the fact that this computation was done correctly. And you can do this all the way to the top. You can keep on aggregating values at each level of the tree, and in the end, you just have 3 people who have signed, so the count is going to be 3, and the product of these 3 public keys. And it comes with a snark proof to say that everything was fine and everything was done correctly. So whenever a specific position in the vector changes, we can update it by rerunning the path from the root, from the leaf to the root. This way, we don't have to recompute the entire proof from scratch. All you have to do is just perform login sized updates to update any change that happens to this data. Another application is what we call as digest translation. Say that there are n values in a vector, and you compute the Merkle digest using hash function 1. For example, that could be SHA-256, and you compute the Merkle digest C2 using Poseidon-based hash function. And we want a proof which essentially says that C1 and C2 were computed over the same set of values. Such proofs are useful in rollups where it's difficult to prove membership over an expensive hash function like SHA. However, you can simply attach a proof saying that, hey, here is the snark proof, which essentially says that these values correspond to the same set of n values that were committed in the vector. So the exact statement which we are trying to prove here is Merkle tree digest C1 and C2 correspond to computed using hash functions H1 and H2 respectively, and these were computed over the same n values. So just like the previous BLS key approach, you can first compute the Merkle digest using the hash function H1, and the map operation in this case is going to just be an identity operator. It's just going to return the same value, and in each level you can compute you have the result of the hash computed using the hash function H2, and there's a snark proof that attests to this correct computation, and you can have this all the way until the top, and essentially pi would serve as the proof that these were computed over the same set of values, but 2 different hash values, 2 different hash functions were used. So we performed a preliminary implementation of our approach using Plonky 2. So recall that the tree-like structure of our approach makes it easy to parallelize, and we noticed that our distributed version can be up to 10x faster than this than the sequential version of our rec proofs. The proof size is 45 KB. However, our aggregation is slower than standard Merkle snarks, where by Merkle snarks I mean that you use Graph16 and Poseidon hash function to prove that there's a set of elements that went inside the batch. Our verification is up to 40x faster than this approach. However, we can update proofs, and we can update a single Merkle proof, the batch proof, in 35 seconds, and it is 43 times faster than Merkle snarks, and it can be up to 135 times faster than Merkle snarks whenever there is a change in the size of the batch that triggers a new setup and a new circuit and so on. So here is the link to our paper. With this, I'll stop and take questions.
Hey, Shravan, thank you very much for very well explained rec proof that you guys have published recently. So something that I also wanted to kind of touch upon as you were kind of explaining how the rec proof works and how they kind of like combine the leaf nodes and then sort of like perform a snark on top of it and then you kind of like stack it up into like an entire Merkle tree with at the end a single snark that represents the entire, so like the batch. One thing I was kind of curious was like, if I wanted to, let's say, reduce the amount of recompute that I want to do whenever I'm updating the batch, right? Let's say the BLS BLS key example that you mentioned, like whenever there's like a new BLS signatures that is coming in, or that the validator sets have changed, that some disappeared and some popped up, for example, um, like there's always like some I guess a minimum bound of like recompute that I have to do because if you follow back the trees, and this is like, oh, I have to recompute this stock, then I have to recompute that stock, and so forth. Um, I was thinking then in that case, would it make sense? Like tell me if this is like some like weird idea, but would it make sense to have like have like a tree that is like non-binary, meaning that you could have like a maybe more than two nodes within uh in like following the one node. Like that, wouldn't that kind of like saves a bit more extra
Yeah, so
compute?
we are in fact working on the generalized version of this. We are working on a k-ary tree, MPTs, and other variants of this tree, and we are trying to get a good sense of how the performance compares. So regarding the stuff you mentioned about multiple updates coming in, you don't have to do each update sequentially. You can put all the updates together, and you can just perform the smart computation once you can do multiple updates simultaneously is the point I'm trying to make. And yes,
I see, I see.
yeah, and yes, you can also think about doing this for different branching factor and so on. So that's something which we are currently working on right now. Yeah.
And when you say like different branching factors, like what kind of trade-offs do you think you would be making with this rec proof?
So the work at each level could become more because you'll have to keep track of
Mm,
multiple things that are happening. So, but
mm.
the tree height, let's say, the tree height could change,
Right, right.
and yeah. So, but at the same time, you can. That's more realistic to what people use in the real world, like MPT trees, MPT tries, and so on. So that will be closer to that. And yeah, this is how it's going to go.
Gotcha, gotcha. And then is it also fair to say that the deeper the tree that you have, the more compute overhead that you may have?
So at each level, you also have to do so. The key thing to notice here is at each level you also have a bunch of smart proofs coming in.
Yeah.
So if your smart proof verification, recursive verification is a lot, then having a large branching factor has to be carefully thought out because you could have more than two proofs to verify that could come in, and that could be if verifying that smart proof is the primary overhead, then that could dominate the cost of doing it.
Gotcha. 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 Okay, sounds good. I think that makes a lot of sense. And I'm looking forward to seeing your I guess explorations on the multiple different versions of like Merkle trees that you will apply rec proof on top as well. So looking forward to that. Great. I think that's all from the questions. And again, Shravan, thank you very much for the time and also explaining the rec proof for us. And yeah, looking forward to the future works. Thank you very much.
It was nice talking to you folks. Thank you.
Thank you.